next speaker. I apologize to everybody, we're running a few minutes behind, but we'll try to make sure we finish up to give you at least a little bit of a break before the OPF session starts. And that's in the other kind of auditorium, so we're not going to hold them up, which is good news. So yeah, we have Molly Rose Kelly-Gorham, who is a PhD student in the College of Engineering and Mathematical Sciences at the University of Vermont, a member of their smart grid program and working on quantification of power system resilience using a data-driven approach. So yeah, thank you, Molly, over to you. We saw your presentation there a moment. It's just
sorry about that.
Dropped out again. Okay, pushed the wrong button. Right,
yeah,
we'll give
exactly.
you a moment to get that back.
How are we? We good?
It's getting there. Here we go. Perfect.
Okay, great.
And we can still hear you as well. Excellent.
Perfect. Thank you for the introduction. I'm going to be talking about using utility outage statistics to quantify improvements in bulk power system resilience. So a little bit different than what we've been hearing so far. This work is a collaboration between the University of Vermont and Iowa State University, and I'd like to take a moment to thank my advisor, Professor Paul Hines, Zhou, and Professor Ian Dobson for all their hard work on this collaboration, and NSF for funding our work. Okay, here you are seeing a picture of Puerto Rico after Hurricane Maria. It's clear that the power system was not resilient to this event. And as the variability of our weather increases, we need power systems to be more resilient to these large events. In order to make power systems more resilient, we need to be able to measure the resilience of power networks and to quantify the effect of resilience of various improvements to the power system. So one approach we could take to measure the resilience of the grid is to write detailed models for the resilience processes and then simulate data from those models, analyze the results, and potentially validate those results with real data. However, given that we have, given that we have, there we go. Given that we have a lot of power system data, another approach we can take, and the one we chose for this work, was to actually directly sample from the utility data to find the outcomes of resilience processes, then use simple models to coordinate between events and to evaluate the metrics. And from there, we can analyze our results. So this allows us to get our results more directly from the data and limit the number of modeling assumptions that we need to take. So in order to measure a resilience event, we need to look at several processes. First, we need to find the initial stress, which is going to cause initial component outages. And then from there, we need to find any cascading outages that have propagated through the network. Next, we need to find the initial load that is shed and to evaluate with that the degradation in the power system performance, and then restore the power system. And since we want to measure the resilience, the last process is to quantify the resilience impact of that event, which we do by integrating over this red area here. So integrating over the unserved load to find the energy not served for the full event. In this work, we're using CRISP, which is a short version of the Computing Resilience Interaction Simulation Platform. This is a new and quite high-level approach which uses utility data to go about quantifying resilience of transmission networks by quantifying all of the resilience processes to many events. We want to use CRISP to quantify the effects of improvements on the overall resilience of power networks. And we include low probability and high impact events that severely impact our communities in the measures of resilience. So the key to CRISP is, to test CRISP, we wanted to ask an interesting research question, and what we ended up landing on was, is the impact of DER, or more specifically distributed photovoltaics and storage, on transmission system resilience? So the real key to CRISP is taking utility data from real transmission system outages so that we can get our results from the data. What we are using are the distribution of the number of line outages, the network distance between lines in a cascade, and the repair times of the lines. The goal is for us to get the results from the data and avoid those assumptions that we could make, would need to make to go about this another way. So one of the advantages of CRISP right now is that we can measure resilience that comes from a ton of different root causes by looking at data and evaluate all of those together. So here, we're just showing the network distance between lines in a cascade. So you can see on the x-axis, the network distance, which goes from 1 to the diameter of the network, and on the y-axis is the probability of that network distance between lines in a cascade. And here, I'm just quickly showing the cascade size distribution. So you can see we have the probability again on the y-axis and the total number of lines out in a cascade on the x-axis. Note that this is on a log-log scale, and in blue we have the utility data, and in yellow we have a zip distribution which has been fit to that data. And last but not least, here we're showing the complementary cumulative distribution function of the component restoration time. So that's the probability of the restoration time being greater than the corresponding time on the x-axis. And note that this data is displayed on a log-log scale as well. All right, so let's take a look at how we would go through a single event in the CRISP algorithm. So step 1 is to sample the number of line outages in the cascade. From there, we can pick an initial line outage, and then we need to sample from the network distances to choose the next lines in the cascade for that event. We also sample generator outages in this work, and I didn't show you data for that because we don't have access to generator outage data. However, utilities with that data can use the same process that we did here, but with their data, of course, for the generator outages and the generator outage time. Here we use a geometric distribution for the generator outages. So step 2 is to find the initial load shedding in the blackout by islanding the network if necessary and using a minimal load shedding optimization. And we're using a DC relaxation for that to find the network performance degradation. And in this work, we assume the generators have grid forming capabilities. So important to know. And from here, we can move to the restoration phase. And once all the components are restored, we can find the impact by integrating, again, that unserved load over the time to find the energy not served. You might notice that there's one less step here than the 5 restoration process I mentioned earlier, and that's because CRISP takes those first 2 steps. So that's the finding those initial outages and then the cascading. We combine them into one step because we're looking at finding the outages after the cascade. Okay, so now all together, I just wanted to show like a flow diagram. So at the top, we can see that we input the network, the sampled component outages. Then we also input aggregate load data, and that's because we're using variable load through the events. And then we input solar data because we want to evaluate the impact of PV, so we need that. Into the minimal load shedding OPF, all of those inputs go, and we find the initial blackout. So from there, we sample the restoration times for the lines and generators, and then we move into the restoration process, which you can see is this loop here. So as needed, we're going to restore any components as the restoration time becomes less than the current time step. And then we're going to find the load shed at the next time step, which we do through a receding horizon minimal load shedding OPF. The reason we're using a receding horizon here over those 2 days is because we want to properly dispatch the storage that we want to evaluate. And then, so from there, once we go through this loop, we have to check if all the components are restored at each step. If not, we save the load shed for that step and continue through the loop until all the components are stored, and then we can integrate over our load shed again to find that ENS, that's energy not served. Here's an example event. So I'm showing you one with just line outages here. So time is going to be on the x-axis. In this top plot, you see the % of load served, and on the bottom plot, you're seeing the number of lines out. So you can see it starts at 100% load served, the load goes down quickly, and then as those lines start to come back online, you can see that the % load served goes back to 100%. So it increases till it gets to 100%, and then the red area is the energy not served. Okay, so it's really important for resilience events to think about both the event size and the event duration. So here what we did is we broke the risk of all the events into bins. So we represent the risk of the bin as the area. The bins are split by size and duration, so to small and large events, and then we have short and long events. And here's an example in the bottom left here showing a small and short event. which while we do consider that to be a reliability event, we still include those in our evaluation here. The energy not served, which is the red area for that event, is considered the cost in the risk, so the probability times the cost, and we're using ENS for the cost. So here's an example of a small size and a long duration event. And then we have an example of a large size and short duration event, and finally, large size and long duration event. Okay, so in order to evaluate resilience, we need to look at many events because all networks will fail to certain events. So we can't just look at one and measure resilience. What we want is the distribution of the energy not served for the network to measure the resilience over all the possible events. And we want to break that information down into which types of events contributed most to the risk. Okay, so now we're going to start thinking about our case study. I just want to let you know we used a 73 bus case. I think that actually was used in the previous talk, although we changed it a little bit. And so I want to show you that the color key is going to be in the upper left, and then we have several different networks that we're evaluating. So we have a base case, this is going to be that 73 bus network. And then as we move to the right here, we have a case with 5% of the load in PV on each load bus. So that's 5% of the load on that bus. And then the capacity of that PV increases as we move to the case that's all the way to the right and on the top. So that case has 20% of the load in PV on each load bus. And then going to the next row here, we have the case with 5% of the load in storage on each load bus. And that's the load of that bus. And then the case, as you move to the right again, with 20% of the load in storage on each load bus. As you move to the right again, we've added PV to that case with the 20% storage already. So 20% of the load in storage and 5% of the load in PV. And finally, in the bottom, right here, we have the 20% of load in storage and 20% of the load in PV on each bus. Okay. So here, we're looking at events that began on a winter night. And I just want to say that clearly for both the load and the solar data. The division between the bins here is such that so between the small and long events is 1 hour, and between the small and large events is 1,000 megawatts, which is about 10% of the load of this network. So here we can see the base case to the right of the color key to compare, and adding PV to the case for these events does not reduce the risk a perceptible amount at least, and we need to remember that this is winter and at night, but we see that adding storage significantly reduces the risk, so that's on the bottom here, especially to the large and long events, and that's the color in dark blue. And you can see by adding PV to those events, those cases with storage, you're still not reducing the risk. Now we're looking at the case where we started the events in a summer day, so both the load and the solar data again. So we can see a small reduction in the risk from adding 5% and especially 20%, of course, PV, especially to the bins with long events. So that's your green and your dark blue here. And we again see the reduction in risk for adding storage. And here we do see again further reduction. You can especially see it in this dark blue color, reduction in the risk to the large and long events when we add PV to that case that already has storage. So here we have the complementary CDF, and this is on a log-log scale. So we have several cases from the bottom row of that last slide that I just showed you. So this is for the sunny day. So in dark blue, we have the base case. In yellow, we have the case with 20% of the storage added. In green, we have the case with 20% of the storage and 5% of the PV. And then in gray, we have the case with 20% storage and 20% of the PV. So we can see clearly there's a significant increase in the resilience of the network from adding 20% of the storage. Note that where the lines are intersecting here, so that is going to be the fraction of lines where the energy not served was not 0. So that's the fraction where the intersection happens there. So we reduce the number of events where there was any energy not served by adding that storage. And we can also see a small further increase in the resilience from adding the PV, particularly in the size of the largest event, which is going to be where we hit the x-axis. So in conclusion, the CRISP simulation is new and a high-level approach to quantify the overall resilience to a power network. We need to model 5 processes to measure resilience, and those include the initial stress and outages, cascading, degraded network state, restoration, and analysis. CRISP samples from utility data to find the outcomes of these processes, and this allows us to reduce the number of modeling assumptions we need to take. Resilience requires us to think over 2 dimensions of event size and event duration, and our results on the impact of DER show that both storage and PV can increase resilience, and we found for the same power capacity of PV and charge storage that storage further increased the resilience. So thank you very much. Love to take questions.
Great, thanks very much, Molly. And yeah, we do have a question from Wakas actually. So Wakas, do you want to just unmute yourself and just ask the question?
Yep, sure. Thanks, Molly. So the sequence in which outages are applied, that makes a difference how the system cascades into a blackout. So are you sampling outages randomly and independently of each other?
So what we do first is we decide how many outages are sampled of line outages, and then from there we pick the initial line, and then we just pick that as a randomly basically. But from there, if there's going to be more lines outage, we use the network distance distribution, so the network distance in a cascade, to then pick the lines. But we don't, between the lines that are of that same distance away, we're not specifically picking one over the other. Does that answer that question? And I totally agree that cascading, we could change this and have a model of cascading, but that's how we're doing it right now.
Yeah, okay. Thanks. I mean, I just want to clarify, if I could, that you're really addressing transmission. Is that right?
Yeah, that's right.
And I'm curious actually about where the data are coming from, because certainly where I live and work in Britain, we see very few transmission events that lead to interruptions to load, and yet you seem to have all this data about you know, how many, you know, how big a cascade is, and how right. You know, how much load is interrupted and how long it takes to restore it.
Yeah, so this is data from BPA, that's Bonneville Power Administration, and it goes back, it's decades, so or at least it's over 1 decade. Sorry, excuse me. So while there are few events, there's enough for us to look right. at in there.
Although, yeah, I'm not sure I'd want to be a customer in that area. There seem to be a lot of interruptions. But then I think that's part of the point, where I think your work does fit into this market context that we've got in the rest of the session, which is, I think it's becoming increasingly important to sort of identify, you know, what new resources are needed to manage these kind of, you know, high impact, low probability type of events. And they're really hard, I think, to set a kind of market signal around.
Yeah, that's a good point. I definitely think we want to build costs further into our model, but it's difficult to do that because so it really impacts people of lower socioeconomic status a lot more, for example.
Unusually, yes. That seems to happen with a lot of things, doesn't it? I've got a question on the chat, actually, also on the Q&A. Yeah, a friend of mine from Imperial College, Magnus Jameson, I think he deserves some kind of special prize. He's probably the only person ever who's survived a PhD with 2 supervisors, one of whom was Goran Strapats and the other of whom was me. So he's saying, this looks like really cool work, thanks for the presentation. Now, given an increase of faults or outages on the system will increase the burden on restoration efforts. Mm-hmm. You know, more stuff broken, fewer people, or the few people that were there are spread out among more effort. Yeah, could there be a way to incorporate that feature into the analysis. So, you know, the restoration gets harder the more outages there are, I suppose, is what Magnus is saying.
Yeah, and I definitely agree with you. And because we end up pulling from that log normal, so I don't know if you noticed, it's like we ended up fitting a log normal distribution to the restoration data. So we pull from that a lot more when there's more component outages, of course. So that's how it sort of gets in there now. And there were a few big cascades that gave us data for that. So.
Okay, good. I'm just going to move on. Sorry, if I could, I'll just go on to the next question. I know we're running out a bit out of time, but I want to pick this one up as well with Dan Molzan, who deserves some kind of special hero award for all of his efforts on the TPC this year. Can you expand a bit on how you're modeling the storage? So is it going to be fully charged, or do they serve the most important loads first, or this kind of thing?
Yeah, they're fully charged, and I should say that I'm not modeling the effects of like frequency changes, right? So I'm not saying they're gonna disconnect if there's a big event, which you can argue over all day for sure, because, but yeah, so hopefully that answers. Also, what does this say? So presumably the storage owners will serve their most important loads first. Oh, I see, that's why you said that. No, we don't have any priority for our loads in this model, at least not as yet.
Right. Okay. It's a good point that it's a work in progress, but it's nice to see where you've got to so far. So Adonis, who I think he wins an award as well for being the best question asker, has put one up there. But we could be here all day answering this one. I think traditional reliability analysis and resilience analysis. I think he's kind of has acknowledged that. So if we did have a virtual pub or a virtual bar, we would all go and pick that question up in that place. So maybe we'll leave it for that and we'll hopefully do it another time. But I think we will need to move on. So thanks again, Molly.